This is Remote Ruby.
Have you any remote idea to the meaning of the word?
Andrew, I don't know your middle name, Mason.
Good. That's how I feel about that. Jason Michael Charnes.
Dang it.
Oh,
Busted.
Man. Yeah.
Busted.
I heard your wife call you that one day.
Yikes. Well, ready to chat while Chris and Brooke are either in the Chicago airport or one of the Chicago airports or on their way to Italy.
Well, at least we're here.
We're here.
Not Italy.
Not soaking it up in the, I was going to say
not
Italian sun, but but they're in a plane. So soaking it up in the
plane. Well, we've got something else to soak up today, right? I'm moving us on from this, wherever you're going with that.
Why? Do you not trust me?
No, I didn't think you were going to land it.
Yikes. So that you didn't trust me. All right. Well, enough about us today. I am thrilled because we have a topic today that actually probably affects a lot of Ruby developers. And I'm sure a lot of people understand a lot about it. I would like to learn more about it, though. And so today we're going to talk with Takashi Kokubun about JIT, just-in-time compilers in Ruby. So Takashi, thank you for coming on Remote Ruby and hanging out with us today.
Hey, yeah, I'm nice to being here.
So I want to maybe back up. There's, in the last 5-6 years, JIT's become a popular term in Ruby, or at least a familiar term. You, if I'm not mistaken, did work on the original MJIT, correct?
Yep.
So before we maybe talk about how we got there, would you mind describing what a JIT compiler is and why we would want to use one in Ruby?
So first of all, Ruby internally has a compiler that compiles Ruby. So first of all, it parses Ruby into a syntax tree, and then the syntax tree is then compiled to bytecode that's specific to Ruby virtual machine. So virtual machine has, for example, instructions like put object and then plus and then leave that's return. So like if you have a 1 + 2 method, then the bytecode looks like put object 1, put object 2, and then those objects are pushed to the virtual machine stack. And then plus the instruction will then pop those two objects from the stack and then calculates the result and then push that back again. And then return leave instruction will return that object from the method to the caller. So that's how interpreter works. But then the problem with that is you have to kind of abstract away the Ruby virtual machine specific implementation from the compiler. So the bytecode is like just some random bytes on the memory, and compiler cannot optimize that well. However, let's say you know that the plus instruction is going to have 1 + 2, then the compiler could know the result is going to be 3 if it's already known. So the thing we could do in the interpreter, one idea is that we could add an instruction that says put this and then plus, which is like combining multiple things. And then that instruction could do more things, optimizing that. Like if the argument is known to be an integer, then you don't need to check that type of those objects. And then if you already know that, plus instruction is not redefined. And then if it's redefined, we are going to expire this instruction. Then you could ignore the redefinition check, or the method dispatch could be ignored in that combined instruction. The problem, however, is that we cannot add those kind of combined instruction for every single operation for every single method. So like there's infinite things we could do for optimizing the interpreter, but if you keep adding those instructions to the interpreter, it's not maintainable. You have to duplicate every single implementation in the virtual machine implementation. So the thing, ideally, we want to keep adding those instructions for every single method. So like we could dynamically generate those instructions at runtime. That's what JIT compiler do, in my opinion. JIT compiler could look at the method and then see that there's a put object plus, then we are going to generate a specific code that's tailored towards this specific method. Then we can do a lot of things that virtual machine cannot do, because virtual machine is designed like it could be kind of maintainable. So like we don't really combine those instructions, because if you do that, it's too complicated. The virtual machine, the way it works is like you have a lot of abstractions. As I said, there's virtual machine stack. But to make it work across different instructions, you have to make it just a pointer on the heap. And then instruction is going to read the memory and then operate on multiple things based on the stack pointer. However, JIT compiler could instead do something like read this stack pointer first and then do something based on that on the compile time. And then after calculating the offset from the compile time stack pointer, we do that without reading the memory on runtime. So JIT compiler could skip reading the memory for those operations because, as I said, we could expire the compiled code at runtime. We could skip some checks like method redefinition, which happens all the time in Ruby. And type checks is also expensive because everything in Ruby is a method call. So you have to do type check and the method dispatch. But that kind of thing could be also removed if you combine those things and also allow the interpreter to remove the instruction after something happens. So that way you can do cross instruction optimization plus runtime code patching is very important for allowing those kind of optimization, which is why you want to use JIT for the optimal performance of Ruby.
That makes sense. So if I'm not mistaken, the JIT came about kind of as the Ruby 3x3 push, correct? When Matt's at RubyConf 2015 said, want to make the goal for Ruby 3.0 is to be 3 times faster than 2.0. Yep. So the first JIT compiler we got was MJIT.
Yep.
And I'm curious, were you there at the beginning of MJIT?
So I became a Ruby committer like in 2014 or so. And then at the time I was already a Ruby committer. And then the time when the MJIT was merged, I think 2016. So Ruby 2.6 was the version that was merged. And I'm Ruby committer as a maintainer of ERB. So still, it's kind of like a compiler. I'm into that kind of stuff. And also, I became an ERB maintainer as a person to optimize the ERB. I'm not really into like extending the syntax. I'm also a maintainer of HAML and Slim, but I'm mainly optimizing those things. So through that experience, I did a lot of Ruby level optimizations. Like we changed the way to concatenate the strings in the template engine. So that's going to be optimal in the Ruby virtual machine. However, as I keep doing that, I had framework. I maintain a template engine framework called Tempo, which is used by HAML and Slim. And that's something like a compiler. So it optimizes intermediate representation specific to template engines and then compile that into a more optimal Ruby code. However, I thought that if there's a compiler that do that kind of stuff on our behalf instead of like letting developers do that kind of stuff, then we don't need to spend time doing that at all. So I wanted to solve that bigger problem. And then I started working on JIT compiler that is not MJIT first. So that was called LLRB. That was a JIT compiler that uses LLVM. LLVM is a technology behind like languages like that. So C language is also Clang compiler uses it, Swift uses it, Rust uses it. So that kind of thing. So I started using LLVM for building Ruby compiler, and then I presented at Ruby KD. But at the same time, in the same year, another guy came up and said, we thought about a way to introduce a JIT compiler to Ruby, and that was the idea of MJIT. So that person was called Vladimir Makarov, and he proposed to replace both the interpreter and the introduce a JIT compiler. The current interpreter was designed in Ruby 1.9, which is designed by Koichi, and that was called YAR virtual machine. And Vladimir, on the other hand, proposed to replace the virtual machine because it's kind of useful for developing a JIT compiler. You could build an interpreter that's more friendly to developing JIT compiler. So that's his design. However, combining interpreter and the JIT compiler, it's actually faster than the interpreter, the original interpreter, but the interpreter alone isn't really faster than the original interpreter. So I was kind of against that because many people are still using the interpreter, and like there's a lot of hurdle to make it stabler and also migrate people to using JIT compiler. So for at least a short midterm, I wanted to keep the interpreter's performance. So then what I did was rewrite the MJIT compiler from scratch, supporting the stack base, the original interpreter, which is written by Koichi, and then with yet another JIT compiler that works like original MJIT in the sense that it uses a sync compiler to generate machine code, but that supports the current interpreter. And also because the experience of developing LLRB kind of helped it, because the LLRB was also based on the original interpreter. So I knew how to deal with a stack-based operation and compile that to another machine code. So that's how the MJIT that was merged to Ruby 3.6 came out. So like another person proposed the idea to generate machine code in C. I didn't like the interpreter removals or replacement. So I kind of rewrote the whole thing. And then I kept maintaining that for 5 years.
I like how you just casually said, oh, I just rewrote the MJIT compiler. Was it hard? I assume that wasn't easy.
Well, yeah, but like I already knew that how every like instruction works. So like I think it was like 1 or 2 months to rewrite the whole thing. So like it wasn't easy, but at the same time, I already had experience doing that by like developing LLRB. So it's not too hard either.
And you said it was Ruby 2.6 that MJIT went in.
Yeah.
What year was that?
2016.
Okay, it's 2016. So what kind of performance gains in Ruby 2.6 did you kind of see on average? I know that depends based on the application, but on average, what could you see using MJIT in production?
So in production, I'd say I assume that the production generally means like Rails applications. And then as of 2.6, we are actually mostly slowing down those kind of workloads, unfortunately. I then learned that like years later, I learned why that happened and figured out how to fix it. But as of the release of 2.6, that was actually slower in my experience. And the things that the like MJIT was focusing on was a different benchmark, which is called Optcarrot. That is a Nintendo Famicom emulator written by another Ruby committer. And then when Matt announced the Ruby 3.3 project and the author of the Optcarrot benchmark stepped up to announce that benchmark, and because he was also kind of famous in the community, that was widely accepted by the community. And then like we were kind of working towards optimizing that benchmark. And then MJIT was specifically designed well for optimizing that benchmark, which I guess kind of contributed to merging that JIT compiler. But at the same time, MJIT was not really good for optimizing RAS applications. So until YJIT came out, MJIT was like kind of struggling to optimize various applications. And then we figured out how to fix it, but that was after YJIT was merged. So I think people almost never use MJIT in production, in my opinion.
Interesting.
Can you say what it was about Rails? Because I remember finding that interesting when I learned about it.
Yeah, that was also interesting for me because I'd been like doing that for years. So the reason why it was slower on Rails was that it uses a sync compiler, and using a sync compiler means that you're going to generate one object for one compilation unit, which is usually a one method. So like if you do that and then dynamically load that using like C library, it's going to be a one memory page per one method. On the other hand, if you build JIT compiler naturally, one memory page has a lot of methods. So like more compact and single cache could have multiple methods. But on the other hand, MJIT can only fit a single method in a single cache. So like it's very memory cache inefficient. So Rails bench uses a lot of methods. So if you call so many methods across various frameworks like ActiveRecord and ActiveSupport and so on, it's going to cost a lot of cache inefficiency. So like Rails is very like method call intensive. You need to call various method calls. On the other hand, Optcarrot was very much intensive in a very specific, a very few set of methods. There's a method to render pixel, to render the screen, and also another method to move the clock. And most of the time, you call the render pixel, move the clock, move the pixel, move the clock. And that, if you are good at optimizing those two methods, you're going to be good at optimizing Optcarrot as a benchmark. So that was kind of easy because that's going to be still 2 memory pages for MJIT. So it's not hard, but for Rails bench, it's going to be as many memory pages as the number of methods. So it was hard for MJIT to optimize those kind of workloads.
So with MJIT being benchmarked against Optcarrot, what kind of improvements did you see in running Optcarrot with MJIT?
So Optcarrot was also instance variable intensive benchmark. So in the render pixel method, you read a lot of instance variable to calculate the next pixel, and then you then store that. It's also integer calculation intensive. Obviously, you have to calculate a lot of pixels. So like, if you are good at calculating the integers and reading and writing the instance variables, it's going to be fast. And the way MJIT optimized it is that MJIT is known for generating machine code by kind of copying the original virtual machine implementation into the generated code. But it's actually not that true in the sense that for things that we want to optimize, we can rewrite the whole implementation and generate a specific C code that's faster than the virtual machine. It's kind of important because if you don't do that, then you are kind of copying the interpreted implementation to JIT code, which almost in many cases, it doesn't really make things faster. So we focus on things that matter, such as instance variables in this case. So for instance variables, we do things like instead of reading the memory to calculate the index for accessing the instance variable, we kind of cache the index of the instance variable and in the JIT code. So like instead of reading the memory, you can directly write this in this instance variable using index 1. So we are going to just read the index 1 instead of reading the memory to check it. So that way you remove a lot of memory indirect operations from the instance variable access. That way, MJIT was still faster than the interpreter in the Optcarrot benchmark.
So you kind of already mentioned YJIT, and that was also big news in the Ruby community when work on that started. And you're at Shopify on the Ruby infrastructure team. Were you already at Shopify when YJIT started kind of being birthed?
When YJIT was built, I was not in Shopify at that moment. I joined Shopify last year when Ruby 3.2 was being developed. So Shopify started to develop YJIT in Ruby 3.1. And so that was released as part of 3.1, but I was not there. So like I was in a position to kind of compete with their team by MJIT. So like at the almost same time, I learned how to optimize Rails bench by changing how MJIT code generates code. So as I said, the memory page inefficiency was tied to how MJIT compiles method into C. So that thing I did was compile the whole set of methods in a single C file and then compile that into a single object and then load it. So that's how you could be loading multiple methods in the single memory page or multiple memory pages together. By doing so, MJIT also successfully optimized Rails bench by something like 5%. At that moment, I learned that how the memory layout is important. You must be loading all methods at the same time instead of generating methods one by one. So it kind of makes the JIT compile development hard. Also, if you compile the whole thing, it takes a lot of time to do the warm-up. It actually takes minutes to compile the whole set of methods. So it's really not usable even if you could optimize Rails bench. And then also, even if we worked hard on optimizing very important pieces, the speed up was only 5%. And part of the reason why I thought that was slow is because you cannot modify the machine code afterwards. So C compiler or C language itself doesn't really allow you to modify or monkey patch particular part of the C code, obviously. You cannot, for example, change things after a method is redefined. That's what YJIT is doing all the time. So like, if you are generating machine code directly instead of using a C compiler, you could do many more optimization on top of that. So I wanted to switch to writing assembly instead of C code because that prevents you from doing a lot of optimizations. So I want to develop YJIT instead of MJIT, or at least I want to generate machine code. So that's why I wanted to join Shopify to develop YJIT. And then I joined Shopify in the next year, 3.2 development.
I just want to take a second to thank our sponsor, Honeybadger. Monitoring like web development can be complicated. There are tons of tools and techniques, but you just want to know that your app is up and your customers are happy. When your customers encounter a problem, you need clear, actionable intelligence, not walls of charts and reams of logs to tail. That's why they built Honeybadger, the monitoring tool we've always wanted. A tool that's there when you need it and gets out of your way when you don't, so you can keep shipping. Know when critical errors occur in which customers are affected, respond instantly when your systems go down, improve the health of your systems over time, and fix problems before your customers can report them. I know from personal experience, I've fixed bugs when they've shown up in Honeybadger and then emailed the customer to let them know, hey, I think I saw you get a 500 error. I fixed it. And I just wanted to let you know you can try again. And it blows those customers' minds to see that they didn't even have a chance to report the bug to you. It's wild. They love it. Honeybadger is the application health monitoring tool built for you, the developer who cares about a quality product and happy customers. Start monitoring today at honeybadger.io. It's free for small teams and setup takes as little as 5 minutes. Once again, that's honeybadger.io.
Okay. So with Shopify, you're working on YJIT. What are some of the differences that YJIT has taken from MJIT? And what are some of the benefits that come from those different approaches?
So as I mentioned, YJIT is directly generating machine code using their own assembler. They wrote their assembler in C and then they're ported to Rust afterwards. And the reason why it's important is because if you are writing the C code, you cannot modify the C code, and then assembler could be patched by reading this. So MJIT is also actually generating machine code, but the problem is you don't know which part of the machine code generated by C code is related to which part. So if you were able to know which part of the generated machine code is related to this C code, you could achieve a similar kind of optimization, but in reality, there's no such C compiler. So you kind of have to generate a machine code so that you take the full control of the position of the code and also the layout. It's kind of related to the Ruby 3.2 feature, which is the code GC, and also the ARM64 support. We changed how the code is organized in the memory layout. So in 3.1, the layout was something like we put half of this code into the first section, and the other section is going to be code that is not often used. So that way, the first section is going to be on the cache a lot of times, and then the other part, which is not going to be used often, is going to be out of the cache. So if you have the full control over the memory layout, you can control how cache is going to be performing efficiently. On the other hand, MJIT is using C compiler, so C compiler decides whatever they want to do. So we don't have full control over how cache is going to behave in the MJIT. So YJIT has multiple advantages over MJIT. Obviously, one is that, as I mentioned, memory cache efficiency, and also code patching is also available. You can know the positions, and so rewrite the thing when method is redefined, for example. And lastly, I think because it's lazy, so the architecture is very much different between MJIT and YJIT. So MJIT takes one method and then compile it, and then it's rolled it into interpret and then executes, resume the execution. On the other hand, what YJIT does is YJIT breaks up a single method into multiple blocks, which we call basic block. Basic block doesn't contain branch. Like if you have a if statement, then the blocks, like instructions before the if and instructions after if is going to be split. That way, you break up a single method into multiple blocks, and then you lazily compile each block one at a time. So when YJIT starts execution, YJIT generates a stub that is a callback to the compiler. So you put a callback to the compiler in the position of the method, and then when interpreter executes, it callbacks the compiler to generate that single block. And then when it reaches branch instruction, it again puts the compiler callback again and again, and then it resumes the execution. So that way, YJIT lazily compiles stuff, only things that are actually executed by that application. Let's say there's a if something which doesn't hold for that Rails application, it's not going to be compiled. So that way, you're also going to have much compact layout, which is more cache efficient to the actual production applications. So like it's also compilation is much faster because you don't need to compile unimportant things. And because you don't go through parsing C language and compiling C function and optimizing that, it's also going to be much faster generating code. So the third benefit of YJIT over MJIT was faster compilation and faster warm-up. And it very much helps Shopify because we deploy applications like every 20 minutes or so. So like we started very fast, and it needs to be very good at warm-up because you deploy that so often. So that's how YJIT is useful, I think.
And with YJIT, it does benefit Rails apps. I mean, obviously, Shopify is many Rails apps. So Makes sense. What kind of performance benefits, gains do you see using YJIT?
In benchmarks, we were seeing something like 50% speed up in Rails bench. But in production, it's not that easy. Like in Rails bench, you can see everything and profile everything, optimize everything. But in production, we need to kind of instrument the production behavior and not profile, but kind of guess what is going on. And so we could optimize YJIT towards our production application and make it faster. But the performance was something like, as of 3.2, that was something like 10% faster in the main storefront rendering application. And then today, I think it's gone up to something like 16 or 18% on average faster than the integrator.
That's amazing. When you were talking about how when you can benchmark against Rails bench and it's 50%, and then you said then you've got to like deal with Rails apps, all I can think of is, then you have to like try and figure out how to optimize all the terrible code that Andrew and I write in our Rails apps. And that's when the real work starts.
Yep.
So that's pretty cool. And now I want to circle back to something you said earlier, which was I want to avoid C and just go straight to assembly, which is something I don't hear a lot about. So not something you're doing with YJIT. Of course, YJIT, you mentioned written in Rust. So that paves the way for, I think, us to talk about RJIT. And I would like to hear more about your work on that.
The moment when I started working on RJIT was the last December. So MJIT was still in a very active development by myself. Like I introduced batch compilation for making overall faster. And also last year, I rewrote MJIT compiler in Ruby. So a lot of things were going on. But when I worked on that very hard, I realized, well, it's still not going to be good at like production workloads because you cannot rewrite C compile and C code afterwards. So like to do things like YJIT, you have to be actually generating the machine code directly. So I wanted to change the architecture so that it's not going to suffer from that blocker. So I kind of secretly started working on RJIT in the last December. And then I kept going on for like 3 months and then kind of popped up on the Ruby developers meeting and said, well, I want to replace MJIT with this thing because this makes things simpler and makes it faster. So that's how I developed and merged RJIT into Ruby. There's actually other motivations to do that. So one is because of how MJIT works, you have to export every single C function that's used by MJIT. And export means other third-party developers could also use that from the C extension gems. So it's not really good in the sense that you have to expose implementation details and you have the risks of needing to maintain the backward compatibility in those interfaces. So we didn't want to export those internal symbols. And at the same time, the way MJIT works is you put like a lot of C codes from the virtual machine implementation into a single C file header, and then you compile the method into using that header. And the header needs to do a lot of weird stuff. Like if this is defined, we are going to ignore this section. And if def is everywhere in the Ruby virtual machine code because of how MJIT works. And once YJIT comes out, nobody really cares about that if def branches. So we wanted to remove those complexity from the implementation. So if the same JIT compiler were rewritten in something like YJIT, then we are not going to need MJIT specific those implementation complexities. So by removing MJIT and putting something like YJIT, you need only something that's needed for YJIT. So the new JIT compiler, RJIT, is reusing what's used by YJIT, something like internal C functions that's not exported by symbols, but still that could be used if you are in the same interpreter. So it needs to use exported symbols because that's loading the C code dynamically. But if you're not dynamically linking, but simply statically linking that as like part of the interpreter, then you can use that without exported C functions. So that way I proposed RJIT was, if you remove MJIT and then introduce this RJIT, you are going to make the virtual machine implementation much simpler. So we want to have this for maintainability. And ultimately, this could also help YJIT because by eliminating those MJIT-related complexity, you could kind of reorganize the architecture towards YJIT and make YJIT faster. And indeed, I actually did that last year and make it very much faster for YJIT. And the other motivation was because I rewrote in Ruby last year, it kind of opened up the secret backdoor for monkey patching JIT compiler. From 3.2, you could monkey patch the JIT compiler to replace that with your own JIT compiler. And people actually started using that. There's Aaron Patterson and Joe Hawthorn. Both of them wrote their own JIT compiler and they plugged their JIT compiler into that interface. So I kind of didn't want to take out their fun out of that project. So like, I wanted to have somewhere that could be monkey patched by those JIT compilers. So by keeping RJIT, we can still continue to experiment with those original JIT compilers. So like there's there for their backdoor and experiment with. So like both John Hawthorn and Aaron Patterson also contributed to YJIT. So they can learn from the original JIT compiler development experience, then contribute back to YJIT. And that's same for me. The purpose of RJIT is not to compete with YJIT, but because my primary focus or main motivation is to make YJIT the best JIT compiler, I want to just learn from RJIT experience and then contribute it back to YJIT. In fact, when RJIT was released, it was faster than YJIT in Optcarrot benchmark, but then I was already aware of why RJIT is faster than YJIT. So I then contributed the benefit back to YJIT this week. And so now YJIT is actually faster than RJIT in Optcarrot.
That's awesome. So RJIT in a way now kind of serves as like a testing ground.
Yes,
to like experiment with different JIT compiling techniques. And then they get, in a way, moved into YJIT, which it sounds like, I'm kind of reading and even hearing you talk today, sounds like YJIT is the JIT compiler you want to use in your real world Ruby apps.
There's a reason for that. So writing JIT in Ruby is so much fun than writing that in Rust. But the problem is if you write JIT compiler in Ruby, you have to generate a lot of objects on memory, and then GC suffers from marking those objects and sweeping those instructions objects. So even if you don't want the application to be impacted by a JIT compiler, the application shares the same garbage collector. So if you compile methods, then you give out of the objects on the memory, and then they cannot be cleaned up. So actually, even if the YJIT and RJIT generate the same code, RJIT can often be slightly slower than YJIT because garbage collection time increases a lot, slightly. And another thing is Rust is obviously faster than Ruby still. So if there are JIT compilers in Ruby, warm-up is also slower. So for environments like Shopify, we want to warm up the application very fast. And the storefront renderer is very performance intensive. So we want that to keep being faster. So Rust can quickly compile methods and make that production performance faster. But RJIT is slightly slower at compiling the Ruby methods. And then, so it's not less like suitable for production performance. Still, it's kind of useful for experimental purposes because once you are done with the compilation, the peak time performance is kind of comparable because after compilation is done, you are going to just execute the machine code generated by Ruby code. So at that moment, the Ruby performance, the interpreter performance doesn't matter because you are just executing the machine code. That's not really related to Ruby code anymore. So the primary use case of RJIT is just benchmark. Like YJIT bench is the primary place that RJIT is going to be used. And the another thing is because RJIT is going to allocate more memory, like memory usage is also important in production. We use a lot of memory in the storefront renderer because we have to load a lot of users' templates and then render that. So it uses a lot of memory, but we don't want to use the size of the reliable memory from the application by using that by Ruby object. So if you write Rust, you can control the size of the object you're going to consume on the memory. But Ruby objects, on the other hand, is less controllable. So memory is also less optimized in RJIT. So like the only thing that RJIT can compete with YJIT is just a peak performance, and other things like warm-up speed and memory footprint and also GC overhead is going to be worse in RJIT. So definitely YJIT is going to be the JIT compiler you should use on production.
I asked you this before the show and you gave a really interesting answer, but I asked you what your experience had been like with Rust. How do you feel about it?
So I have mixed feeling. One is it has a very good editor support. I use both VS Code and NeoBeam, but those have both great support by Rust Analyzer. It's great that you can just rename the symbol and every file related to that can be changed safely. And if you want to reorder the arguments, it's kind of easily done. But in RJIT development experience, when I realized that, I learned that very after immersion that by flaky test failure. So those kind of comfort or stability in the development experience is much better in Rust. On the other hand, when it comes to writing Rust, there are a lot of kind of challenges. For example, you have to write a lot of casts when you use integer operations. So you have various kinds of integers compared to Ruby. Ruby has only float and integer because bigdam is kind of combined into if exam later before. But Rust, on the other hand, have various types. Depending on the size of the integer, bit type, number of bits you are going to maintain, it's going to be like I8, tiny 8-bit, and U8, and I16, U16, and you actually want to use all of them. So like if you want to maintain the minimal memory overhead YJIT would like to do, you have to use all of them and kind of cast that all the time. Rust wants to be very strict about those types. So if you don't say this type is going to be this thing, they don't allow or they don't compile that for you on your behalf. So you have to say this was I8, but at this moment we want to use that as U6, and you want to say foo as U8 and then ampersand parenthesis end and then R as U size, and that kind of code is everywhere. So that is making YJIT code kind of ugly, in my opinion. And the other thing is one of the biggest difficulties in writing Rust is move semantics. So with move semantics, you have to keep the one reference to one thing unique to that place. And then every other thing needs to be either borrow or mute borrow. And then mute borrow can be done only by one place. So by doing that semantics, there's only a single place that could modify that object. But if you like write program in Ruby, you don't need to fight that kind of stuff. And so you could naturally write some logic and still share the object. But because when it's not multi-threaded, you don't need to really worry about data race or multiple things writing to the same thing at once. You are kind of need to fight the problem that doesn't exist in Rust. And when you start using a complex types like RC, which is a reference counted object, you can also borrow from the multiple places, but the error is going to be runtime failure, even if you are writing Rust. So you are writing Rust for safety, but at the same time, if you start using that kind of types, it's going to be just a runtime failure, which is no different from other languages. So like you have to kind of be very careful about how you write code. For example, you cannot do things like receiver and return object is going to be the same object because that's a sharing. But Ruby could do that kind of thing all the time. So if you are too used to writing that kind of pattern in Ruby, then you will have some problems writing Rust because that's not possible. So lastly, another thing is we are integrating Rust code into C code because interpreter is written in C and YJIT is in Rust. But integration between C and Rust is kind of awkward because you have to always say it's unsafe. Unsafe brace something, unsafe. So unsafe is everywhere. And in the standard Rust convention, you have to say / safety : something whenever you use safety. So safety and unsafe is kind of everywhere if you integrate Rust code into C. And there's also awkwardness in the integration because you cannot share the same struct with C code because Rust cannot understand C code. So like if you want to touch or operate on C structs, you have to prepare a C function that's specifically accessing the C structs field. So like YJIT code is something like get some field parentheses, and these kind of functions are everywhere. On the other hand, on RJIT, because we could generate something that interacts with C better than Rust bindgen, you can do something like method chain, like something dot something dot something. So Ruby code is much cleaner than Rust code because of how we integrate Rust into C code. So you could have nice Rust experience if you are only writing Rust and rewrite every single C code into Rust, but Matt doesn't want to rewrite everything in Rust. So we are kind of stuck with this unsafety and also like weird C struct access situation.
I feel a lot better about that code I showed you, Jason, where I was like, this is some janky code, or looks a little weird is what I think I said to you. I'm like, maybe it doesn't look that weird. Still Ruby. Any kind of exciting things coming in the JIT world you want to share with us?
Sure. In YJIT, I'm working on a kind of big project that is a digital allocation. So even in the Ruby 3.2 or 3.1, 3.2 actually, there was a register allocator. So register is part of the CPU that's faster than using memory. So if you are using a compiled language like C, compiler is going to assign registers to some operations you're doing automatically on your behalf. But Ruby, on the other hand, uses memory by default because it's built as a virtual machine, and C compiler doesn't know how to deal with the virtual machine operations. So everything needs to be abstracted away as a memory on the heap. So YJIT is kind of incrementally developed. So we are using memory by default for most of the things, but we are slowly adapting registers for those operations. And that makes the language so much faster because every faster language uses registers for a lot of operations. That's why they are faster than languages that are mostly working on memory. So the reason why Ruby used to be slow is because they are using memory most of the time, but we want to shift towards using registers. So there was a register allocator for Ruby 3.2 that is to use the register for cross-instruction operations, such as if you as the example said before was like put object plus return. So put object puts something on the stack. So when something like plus operation returns something, we can write that to the register and then use that and to return that, write that back to memory. But for the intermediate temporary values, we were able to use registers for those kind of operations. That's how Ruby 3.2 YJIT worked. But in 3.3, we want to expand that towards something like Ruby local variables. So Ruby local variable is still on memory for Ruby 3.2 YJIT, but for 3.3, we want to use registers for Ruby local variables. You should be using local variables a lot in writing Ruby codes. So every Ruby local variable access could be faster if you have a register allocator to those things. It's not that simple because there's a method like binding local variable get. So like if you just keep everything in register, then it's going to break. So we have to be careful about how to escape those kind of things from the register. But by kind of dealing with that complexity, we are slowly shifting towards using registers in those areas. And I'm kind of focusing on that in my project these days. So like Ruby 3.3 is going to have register allocator for those things. And I already merged one thing that's register allocator to the virtual machine stack. So put object pushes something to stack. And in 3.3, it's going to be written to register. So it's not going to be slower by using memory. So that's how Ruby 3.3 YJIT is going to be significantly faster than 3.2.
Does ERB get any benefit to the work in YJIT or the stuff that's happening in YJIT?
Kind of. So like these days, I'm not touching ERB at all, but like YJIT optimizes string computations by introducing a very special optimization towards string computation methods. So it does a lot of operations on the intermediate variables and then also do a lot of stack manipulation as well. So for those stack manipulation, the register allocator for the stack operands is going to replace the operands from the memory to registers. So they are like ERB operations is going to be faster as well by those optimizations.
If you had to pick a template language, if I was like, hey, I need you to write an app, framework agnostic, what template language are you using?
I'm still using HAML. Like I maintain Ruby Bench website that is benchmarks multiple JIT optimizations, which is a rubybench.github.io. And it uses HAML because I love using HAML.
Yeah, I love it too. You have a HAML package. I don't remember what it's called specifically, but it was like a faster HAML, right? Yeah.
So that's called Hamlit. Hamlit is a template engine that I authored and maintain. And when that was released, that was 7 times faster. And the most important thing of that was like, it was slightly faster than Slim as well. People were kind of moving from HAML to Slim because that's faster. But now you have to move from Slim to HAML because that was faster. And then last year, HAML 6 was released, and HAML 6 was kind of copying. So I'm also a maintainer of the HAML. And then from the HAML 5 release, I joined the maintenance of HAML, and then I kind of replaced a part of the HAML compiler, and then it became like 5 times faster than the original HAML 4. And then in HAML 6, what we did was, and the author came and said, well, we should just replace the implementation with Hamlit. So like we copied the Hamlit implementation into HAML 6 and then just renamed the Hamlit to HAML. And then that's how HAML 6 works. So it's just Hamlit today.
That's awesome. You've mentioned that you maintain all these libraries. you're working on YJIT at Shopify, and then you're coming home to write assembly code. How do you have time for all of this?
I'm kind of juggling project towards multiple time frames. So if you look at the HAML repository, I'm not that active these days, but when I find critical problems, I just come to and merge that. So like my focus is kind of shifted sometimes. And so like right now I'm focusing on RJIT, but prior to that, I was like focusing on the HAML replacement project. So I actually making a lot of other things as well. So like I need to kind of move and then jump in when it's important. HAML 6 was important when that could be replaced by that because of that was said.
I feel like there's a lot of wisdom in that you said so simply. I feel like I could learn from that.
Well, thank you for all your work on Ruby
for real.
And the projects you have going in the community like HAML, things like that. Yeah, just really appreciate that type of work and excited to see the work y'all continue to do. Where can people who want to interact or find you online, where can they go?
So I'm kind of active on Twitter, twitter.com/K0Kubun. That's Kokubun with all replaced with 0. And I'm also on Mastodon, but I'm less active, but you can still follow me on there. And I'm also on the GitHub in the same ID. And maybe you could interact with me. If you want to talk about the GitHub specific project, then you could just file an issue. And then I almost always monitor that GitHub notifications. So you can talk to me in either Twitter or GitHub, depending on the subject.
Awesome. Will you be at Ruby or RailsConf this year?
I'm not going to be on those conferences because I have a 2-year-old kid and my wife is going to be angry if I leave her. So the only thing Understood. I can do is I can go to Ruby Kaigi because my hometown is Japan. And so if we go there, her parents can help her. So like we can go together and do that. So the only conference I can go is just Japanese conference.
Hey, that's cool though. Ruby Kaigi is my bucket list conference.
Yeah, same. I've always wanted to go.
Well, I'm very appreciative for your time today and your knowledge. It's been fun to chat with you and I hope we get to do this in the future soon.
Bye, everyone.